We are approximating CR maps between open subsets of Rn with C-infinity maps. The approximations that we retain are essentially approximations for the weak topology, meaning that if we consider a compact subset of the domain of definition of our initial map, then the approximations have derivative of order up to R as close as we want to the derivatives of the initial map in the fixed compact set. But we want to go a little bit further. We would like to obtain approximations of the initial map for the CR strong topology. The strategy that we are going to follow is very simple. On the one hand, we already know that we can approximate our initial map with C-infinity maps as much as we want, okay, in compact sets, in the sense that we already discussed. We want to have derivatives of order up to R of the approximation very, very close to the corresponding derivatives of the initial map. And then these approximations that we found for different compact sets, we just have to paste it somehow. And as usual, in order to do that, we are going to use partitions of unity. In this way, we are going to obtain the density of C-infinity maps for the strong topology, which is kind of a local result for the strong topology. Now we are going to show the next result. It's an approximation result. Let U and B open subsets of Rn and Rn respectively. Then the set of C-infinity maps from U to B is dense in the set of CR maps from U to B, where R is greater or equal than 0 and smaller than infinity. Of course, we are considering the strong topology in the set of CR maps. And the first thing that we are going to point out is that the set of CR maps from U to B is an open subset of CR it's an open subset of the set of CR maps from U to Rn. And as a consequence, this, of course, is an open subset for the strong topology. This is not very difficult to check out. And as a consequence, we can suppose that B is equal to Rn, right? So we have differentiable maps between U and Rn. Okay, now let us fix F as CR maps from U to Rn. And let us consider a subbasic neighborhood of F. So something like this. Let's remind ourselves that K is indeed a locally finite family of compact sets. Okay, it's a locally finite family of compact subsets of U. And that epsilon is a family of real positive numbers. Okay, so this is going to be a subbasic neighborhood. And what we want to show actually is that no matter what is our choice of K and epsilon, so for every K and for every epsilon, what we have is that this subbasic neighborhood has non-empty intersection with the set of C-infinity maps from U to Rn. Okay, that's the goal. So again, K is a locally finite family of compact subsets of U, but we can suppose that the family is indeed a cover of U. We can suppose that the union of Ki is indeed the whole U. This can be obtained, for instance, by considering more compact sets. And in that way, this set over here is going to get smaller because we are adding more conditions. And so if we prove that this intersection is non-empty, it's still non-empty for the original neighborhood. So we can suppose it's not a big deal that the Ki's are actually a cover of U by compact sets, right? Another thing that we are going to do is we are going to consider C-infinity functions, yes, from Rm to, let's say, the closed interval 0, 1, such that these functions are equal to 1 in Ki, and the function is equal to 0 outside of a small neighborhood of Ki that we are not going to make more precise. So this, in particular, what we have now is that we can suppose that the supports of the mu I are indeed a locally finite family. Okay? Very good. So we can define lambda I as mu I divided by the sum of mu j for all j. The denominator makes sense because the supports of the mu's are indeed the elements of a locally finite family. So every sum that we are considering is indeed a finite sum. And and moreover, every point is in some Ki, and mu I in Ki is equal to 1. So every point is in some Kj, and mu j in Kj is equal to 1. So this sum is always positive. So this function over here is indeed a C-infinity function from Rm to the non-negative real numbers. And it's a partition of unity because the sum of all the lambda i's is obviously equal to 1. Moreover, we have that Ki is contained in the support of lambda I, okay, which is obviously contained in U, because the support of lambda I and the support of mu I are the same. So if the small neighborhood of Ki is really small, the support of mu I or lambda I is going to be compact. So this set over here is indeed a compact set, right? And this happens for every I. Very good. Now we are going to consider convolutions. So given f, okay, given given G, or not given F. What we are going to consider is a map GI defined in some open subset of U, whose target space is Rn, and which is going to be the convolution of some convolution kernel and F, right? And what are we going to get? Okay, so we have Ki is contained in the support of lambda I, which is contained in U, right? We have that. And this set over here is compact. Okay. And now what we want is consider Gi as a convolution of some theta and F, right? But if by considering theta with a very small support radius, what we have is that the derivatives of order up to R of F minus the derivatives of order up to R of G sub I, okay, this is going to be smaller or equal than some alpha I that we are going to specify later on. And that's going to be for every X in Ki, for every I in the index set, and for every K between 0 and R, right? What we get is that if we consider some theta whose support radius is really small, what we're going to get is that this support of lambda I is contained also in Ui, right? And fixed a positive real number alpha I, we are going to have this inequality if the support radius is small enough. So for now, we're not going to specify the alpha i's, but we are going to consider alpha i's generic, and we are going to define a specific alpha i's at the end of the proof, right? Okay, so now we are going to define G as the sum for I in the index set of lambda I times Gi, right? That makes sense because Gi is defined in Ui, and the support of lambda I is actually contained in Ui. If the support radius of this theta over here, indeed it should be theta I, right? It's a convolution kernel that is going to depend on I. And since the support of lambda I is contained in Ui, this function over here is C infinity for every I. The support is contained in the support of lambda I. The family of supports of the lambda I is locally finite, so this sum makes sense. It's a sum of C infinity functions, and as a consequence, it's a C infinity function. So we have a C infinity function defined in U, and whose values belong to Rn, right? Now we need to show that G is indeed a good approximation of F if the alpha i's are indeed small enough, right? So here we have the product of lambda and h. Lambda is a function, h is an application, okay? It's an application from some open subset of R. Indeed, it's an application, yeah, from some open subset of Rm to Rn, right? And what we want is considering over here derivatives. Of course, here we should consider components of the h, but okay, right, we are abusing a little bit the notations. And we want something like this. We want to consider partial derivatives, okay, of order k, where k is less or equal than r. And this is going to be a polynomial in the partial derivatives of lambda and h of order small or equal, smaller, less or equal, sorry, than k. Okay, that's what we are going to have. As a consequence, if we want actually to consider estimates, upper estimates for derivatives of lambda times h, this is going to be, because this polynomial actually does not depend on lambda or h, is going to be smaller or equal than some universal constant, some positive universal constant. And here we are going to have the maximum from L equals 0 to L equal k of derivatives of lambda, and here something analogous with derivatives of h. Okay, for instance, we could consider the norm for the first derivatives as the supremum of all the first derivatives in some compact set, something like that. So here we're not specifying where we are actually working, but we are always going to have this kind of formula when we evaluate at a point, right? And this is going to be really important. So we are going to define A, this capital A, as the maximum of A0, A1 till AR. R is, let us remind ourselves that F was a CR map, okay? We are trying to find a C-infinity map in a neighborhood of that F. We are going to define here lambda I, which is going to be a subset of lambda, and indeed is the subset consisting of the points of lambda such that ki intersection, the support of lambda j, is non-empty. This subset of lambda is finite because the family of supports is locally finite, and so there are just finitely many supports that intersect any compact set, okay? So we are going to call Ni the cardinal of this finite set, right? And now we are going to define mu I, which is going to be the norm of lambda j in ki with respect the norm for the CR norm, if you want. You can think of this as the maximum in ki of all derivatives of lambda j up to r, okay? So, okay, and here j belongs to lambda I, all right? This is finite, okay, because ki is compact, and here this set is finite. So there's no problem with that. And we are going to define also beta I as the, so okay, here in order to do these things right, this should be the maximum, right? Okay. And beta I is going to be the maximum of alpha j. The alphas, we didn't define them yet, but even so, if we consider any family of alphas, we can define other constants as a functions of them. And in this way, we are defining beta I. Beta I is going to be the maximum of the alpha j's when j belongs to lambda I. Since lambda I is finite, this is well defined too. Okay, and now with all this data, let us consider the kth derivative, okay, of f minus the kth derivative of g. And for some point x, that it's going to be a point of ki. Okay, we want to consider that. Very good. Of course, k is going to be some number between 0 and r. So here we have some derivative of f minus the derivative of the sum of lambda j times g sub j. Since we are considering just points in, we are considering points in ki, what happens is that lambda j of x is always 0 except if j belongs to lambda I. And we are going to use that. First of all, let's write down f as the sum of lambda j and f, okay? Very good. And this is going to be the sum of the derivative of lambda j of f minus g sub j. Okay, and everything at x, where x is a point of ki, right? Good. As I said, these lambda j's over here are 0 in a neighborhood of x, except if j belongs to lambda I. So, in order to estimate this expression, again, let us make clear that x belongs to ki. Okay, what we have is that this is the sum of the differential, and here we have to consider lambda j times f minus g sub j, but we can consider just j in lambda I, right? And now we are going to estimate this. Here we have a sum in which we have mi terms. So this is going to be smaller or equal than mi times a common estimate that we are going to find for this. But this is the product of a function and a map. So we know that that's going, the estimate for the k derivative is going to be less or equal than ak, capital AK, okay? but here we have that the capital A's are less or equal than capital A. So here we're going to have A, and now we want to give estimates for the derivatives of order up to k of lambda j when j belongs to lambda I and x belongs to ki. But that's somewhere, because that's exactly what we have here. That's going to be less or equal than mu I. So here we have mu I. Okay. Very good. And finally, we need to give an estimate for this, for the derivatives up to order R. But indeed, what we know by construction is that for j sub j, this difference in the support of okay, and here I think it could be a better idea to consider here the support of lambda I, right? We can do it for the same price because we can do it for every compact subset. And what we have is that the difference of this difference has norm less or equal than alpha j in the support of lambda j, right? Our point x is in ki and also in the support of lambda j. So this, what we are going to have is that this difference, when the index here is j, is going to be smaller or equal than j. And we have now that the maximum of alpha j when j belongs to lambda I is beta I. So this is bounded by above by beta I. Okay? This we have this expression. And now let us write here again what's the expression for beta I. Beta I is the maximum of alpha j when j belongs to lambda I. So if we consider very small alphas, we get very small betas. And the point is that we can choose a family alpha I of positive real numbers such that mi times a times mu I times bi is smaller than epsilon I. But in this situation, okay, what we get, because here, of course, this is valid for every k from 0 to r, what we get is that this is smaller than epsilon I for every x in ki, for every index, and for every k between 0 and r. And indeed, that is the definition of our open subset, the subbasic neighborhood associated to F, the family of compact sets K, and the family of positive real numbers epsilon. And so, since G is C infinity, we get that this subbasic neighborhood has non-empty intersection with the C infinity functions, because indeed G belongs to both of them. And so, in that way, we proved that any open subset of the set of CR maps contains a C infinity map. And so C infinity maps are dense for the strong topology in the set of CR maps. Okay. We saw the density of the set of C-infinity maps in the space of CR maps for the strong topology when the source and the target spaces are open subsets of Euclidean spaces. What we want to show now is a global version of this result in which the source and target manifolds are no longer required to be Euclidean spaces. They can be any manifolds. And that's the kind of topic that we are going to discuss in the next lecture. We are also going to discuss another problem, which is the following. If we have a CR manifold, is it always possible to give a structure of C-infinity manifold that is compatible with the CR structure? If that could be the case, and indeed it is, that could allow us to consider essentially that every manifold is a C-infinity manifold, which is actually something very useful. And indeed, we will see an application in next lecture with this idea we are going to obtain as an extension of the Whitney embedding theorem. Thank you for your attention.